You've been lying here, running the same thought again, the one you already know by heart. Your brain has a name for what keeps that loop running. It isn't weakness and it isn't worry. It's a system that was built to protect you, still running long after the threat has gone. The science has been tracing it for decades. The mind doesn't stop editing just because you asked it to. It edits when it's safe. It edits when it's quiet. It edits when you sleep. The part that changes everything. Trying harder, while awake, often locks the pattern in place. The only window where the editing happens without resistance, without you needing to do anything at all, is the one that opens every time your eyes close. Welcome to Sleepy Science. Tonight begins in the dark, where the work is already done before you know it started. Close your eyes and breathe slowly. You're resting where the brain does its quietest and deepest labor. Let your mind release the thought it was still holding. And now we begin. Every night, while you sleep, your brain performs a process that no amount of willpower during waking hours can replicate. Neuroscientists call it memory consolidation. The brain takes everything you experienced, everything you felt, and every pattern you've been running, and begins selecting which ones to strengthen, which to weaken, and which to quietly dissolve. This process doesn't ask your permission. It doesn't require your effort. It begins automatically, within the first few minutes of sleep, following a sequence that evolution has been refining for hundreds of millions of years. The subconscious mind is not a locked room. It is a workshop, and sleep is the only time the workshop is fully open. The word subconscious was popularized by Sigmund Freud in the early 20th century, but the science behind it has evolved enormously since then. Modern neuroscience no longer thinks of the subconscious as a hidden layer beneath awareness. It thinks of it as the vast majority of the brain's actual processing, roughly 95% of cognitive activity, including habit formation, emotional response, and the interpretation of sensory data, happens below conscious awareness. The 5% you experience as deliberate thought rides on top of an enormous automated system that runs continuously, day and night. Sleep is the maintenance window for that system, the only time the automated processes slow down enough to be meaningfully reorganized. Sleep is divided into distinct stages, each with a specific role in how the brain processes and reorganizes information. The stages cycle roughly every 90 minutes throughout the night. Stage 1 is the lightest, a brief threshold between waking and sleep. Stage 2 is where the brain begins its consolidation work, marked by bursts of electrical activity called sleep spindles. Stage 3, slow wave sleep, is the deepest, the stage where the most fundamental restructuring of memory and emotional experience takes place. And REM sleep, which becomes longer in the later cycles of the night, is where emotional memories are specifically processed and often softened. Each stage contributes differently to the overnight rewrite. Sleep spindles are brief, rhythmic bursts of neural activity that appear in stage 2 sleep. They last between half a second and 3 seconds, and they occur dozens to hundreds of times each night. For decades, they were considered relatively unimportant, a side effect of the brain transitioning between states. But research over the past 20 years has changed that view entirely. Sleep spindles are now understood to be one of the primary mechanisms by which the brain transfers memories from the hippocampus into the neocortex, where long-term patterns are held. More spindles mean more transfer. More transfer means deeper, more stable changes to the underlying patterns you carry. The hippocampus is a small, seahorse-shaped structure in the medial temporal lobe, and it serves as the brain's temporary holding space. During the day, new experiences are encoded there first, quickly, imperfectly, still tied to the emotion and context in which they were formed. Sleep is when it offloads. During slow-wave sleep, the hippocampus replays the day's experiences at high speed, far faster than they were originally lived, sending compressed versions to the neocortex for long-term storage. What gets replayed most is not random. The brain prioritizes what was emotionally significant, what felt threatening, and what remained unresolved. The loop you were running before bed is almost certainly among the first things replayed. The neocortex is the brain's outermost layer, the wrinkled surface that makes human cognition possible. It is where long-term beliefs, habits, identity patterns, and deeply held interpretations of experience are stored. For a long time, neuroscientists believed the neocortex was essentially fixed in adults, that its patterns, once formed, were permanent. The discovery of neuroplasticity changed everything. The neocortex continues to remodel itself throughout life, strengthening connections that are used repeatedly and pruning those that go dormant. Sleep is when most of this remodeling happens. The slow oscillations of deep sleep create the precise electrochemical conditions needed for synaptic connections to be added, removed, or recalibrated. Reprogramming, in the most literal neurological sense, is a sleep-dependent process. One of the key mechanisms behind overnight emotional change is a neurochemical shift that happens specifically during REM sleep. During waking hours, norepinephrine, the brain's primary alarm chemical, is present in measurable amounts throughout the cortex. It keeps you alert, reactive, and sensitive to threat. During REM sleep, norepinephrine drops to its lowest levels of the 24-hour cycle. This chemically unique environment allows the brain to re-examine emotionally charged memories without triggering the full alarm response they normally produce. Matthew Walker at the University of California, Berkeley, has called REM sleep a form of overnight therapy. The brain replays difficult experiences in a neurochemical bath that strips away the emotional charge while preserving the factual content. The amygdala is an almond-sized structure at the center of the brain's threat detection system. When you encounter something frightening, stressful, or emotionally significant, the amygdala activates rapidly and stamps that memory with urgency, a neurological signal that says, "This one matters. Hold on to it." At night, the amygdala's activity shifts. During REM sleep, it remains active, but in a different mode, more associative, less reactive. It revisits emotionally tagged memories, not to reinforce the alarm, but to cross-reference them with older, similar patterns. looking for context or resolution. Each visit lowers the emotional charge attached to the memory slightly. Over multiple nights, the charge diminishes substantially. The prefrontal cortex, the region behind your forehead responsible for rational thought, planning, and emotional regulation, has a complex relationship with sleep. During the day, it acts as a brake on the amygdala, dampening emotional reactions through conscious regulation. But this regulation is effortful. It requires attention and energy, and it works less well when you are tired, stressed, or overwhelmed. During REM sleep, the prefrontal cortex's regulatory role shifts. It relaxes its top-down control, allowing the emotional processing systems to operate more freely. This is not a loss of regulation. It is a different kind, one that allows emotional patterns to be reorganized in ways that conscious effort cannot access. The default mode network is a set of brain regions that activates when you are not focused on the outside world, when you are daydreaming, remembering the past, imagining the future, or thinking about yourself. It runs almost constantly in the background of waking life. During sleep, it does not simply shut down. It continues to process, but differently. During REM sleep especially, the default mode network shows patterns of activity that closely resemble those seen during autobiographical memory recall, as if the brain is reviewing the narrative of your life, updating the story in light of new experience. The subconscious rewrite is, in part, a story being quietly retold. Slow oscillations are large, synchronized waves of neural activity that sweep across the cortex during deep sleep. They move like tides, a wave of activation, followed by a wave of silence, repeating roughly once per second. For years, these oscillations were thought to be a passive byproduct of the brain resting. Recent research has established that they are anything but passive. Slow oscillations actively coordinate the timing of memory transfer between the hippocampus and neocortex. They create precisely timed windows during which hippocampal replay is synchronized with cortical activity, ensuring that replayed memories arrive at the neocortex exactly when it is most receptive. The overnight rewrite runs on a clock, and the clock is these oscillations. The concept of synaptic homeostasis offers a compelling explanation for why sleep feels like a reset. During waking hours, the brain's synaptic connections grow stronger with every new experience. By the end of the day, the system is saturated. Synaptic homeostasis theory, developed by Giulio Tononi and Chiara Cirelli at the University of Wisconsin-Madison, proposes that one of sleep's fundamental functions is to downscale these connections globally, reducing overall synaptic strength so that the signal-to-noise ratio is restored. The connections that matter most, those most active during the day, are preserved. The weaker, noisier connections are trimmed away. Sleep, by this model, is not just filing, it is also clearing. The relationship between sleep and emotional memory is not symmetrical. Sleep does not process all memories equally. Research consistently shows that the brain prioritizes emotionally negative memories for overnight processing. Threats, conflicts, unresolved tensions. And social failures receive more replay time than neutral or mildly positive events. This evolutionary bias makes sense. Negative events carry the most survival-relevant information. But it also means that the loops most likely to keep you awake at night are precisely the ones the brain most wants to process once you fall asleep. The thing you cannot stop thinking about is the thing the sleeping brain most urgently needs to work on. Fear extinction is the process by which a fear response gradually diminishes when the feared stimulus is encountered repeatedly without the anticipated negative outcome. It is the neurological basis of exposure therapy, and it is central to how trauma and chronic anxiety are treated clinically. Fear extinction is dramatically more effective after sleep. Studies using conditioned fear paradigms consistently show that sleep between learning and extinction accelerates the reduction of the fear response. The brain does not simply forget the fear during sleep. It learns a new relationship with it. And that learning requires the specific neurochemistry of sleep to consolidate. Theta waves are slow electrical oscillations between 4 and 8 cycles per second that appear prominently during REM sleep and during moments of active memory processing. They are associated with the hippocampus and are thought to provide the timing signal that coordinates when memories are replayed during consolidation. Theta activity is also elevated during the hypnagogic state, the brief threshold between waking and sleep, when the mind is still somewhat aware, but the body has begun to relax. This transitional state is neurologically unusual. The brain is simultaneously capable of conscious thought and the kind of loosely associative processing that typically only occurs in dreams. It is the state most often associated with sudden insight and the resolution of problems that resisted solution while fully awake. The glymphatic system is the brain's waste clearance network, a series of channels that run alongside blood vessels, using cerebrospinal fluid to flush out metabolic byproducts accumulated during waking activity. First described by Macon Nedergaard at the University of Rochester in 2013, it operates almost exclusively during sleep. During slow-wave sleep, the brain's cells shrink significantly, widening the channels and increasing the flow of cerebrospinal fluid through the tissue. Among the waste products cleared is amyloid beta, a protein associated with cognitive decline when it accumulates over time. Poor sleep impairs this clearance. Note: the glymphatic system's full clinical implications in humans are still under active investigation. The relationship between sleep and habitual behavior runs deeper than most people realize. Habits are encoded not in the hippocampus, but in the basal ganglia, a cluster of structures deep in the brain that automates frequently repeated action sequences. Once a habit is encoded there, it becomes largely automatic and highly resistant to conscious modification. Sleep plays a role in this encoding. Research on motor skill learning, practicing a sequence of finger movements, consistently shows that performance improves significantly after sleep, even without additional practice. The automated pattern deepens overnight, not through repetition while awake, but through consolidation while asleep. Emotional regulation, the ability to modulate the intensity and duration of emotional responses, is one of the most sleep-sensitive cognitive functions. Even one night of partial sleep deprivation, defined as sleeping 4 to 5 hours instead of the usual 7 to 9, produces measurable increases in amygdala reactivity. Studies at Harvard Medical School and the University of California show that sleep-deprived subjects respond to mildly negative stimuli, with amygdala activations 60% stronger than rested subjects. And the prefrontal cortex's ability to modulate that activation is simultaneously reduced. The result is a brain that is more reactive and less able to regulate its own reactions. Not because of any failing, but because the overnight recalibration did not fully complete. The timing of sleep matters as much as its duration. The brain's sleep architecture is not uniform across the night. Slow-wave sleep, where the deepest memory consolidation occurs, is concentrated in the first half. REM sleep, where emotional processing is most active, becomes progressively longer in the second half, with the final REM cycle sometimes lasting 45 minutes or more, cutting sleep short by 2 hours. For example, disproportionately reduces REM sleep. A person sleeping 6 hours instead of 8 may lose up to half of their total REM time. The emotional processing that would have occurred in those final cycles simply does not happen. Stress hormones and sleep have a bidirectional relationship that can either support or undermine overnight processing. Cortisol follows a natural daily rhythm, highest in the morning, lowest in the late evening. This low cortisol window is what makes it possible to fall asleep and enter the deep stages where consolidation occurs. Elevated cortisol at night, from late-night stress or prolonged worry, disrupts this window. It delays sleep onset, reduces slow-wave sleep, and fragment REM cycles. The irony is structural. The nights when emotional processing is most needed are also the nights when elevated stress hormones most interfere with the brain's ability to do that processing. Dreams are not random. They are not meaningless noise produced by an idling brain. The neuroscience of dreaming has shifted dramatically over the past 3 decades. From viewing dreams as byproducts of sleep to understanding them as an integral part of the consolidation process. Dreaming occurs primarily during REM sleep, and the content consistently reflects recently encoded emotional experiences, unresolved concerns, and patterns the brain is actively working to integrate. The dreaming brain does not replay memories exactly. It recombines them, placing familiar elements into unfamiliar contexts, searching for connections that waking thought would not easily make. This recombinatory process is one mechanism by which the emotional charge of difficult memories is gradually reduced. The hypnagogic state, the threshold between waking and sleep, has fascinated scientists and artists for centuries. Thomas Edison reportedly kept a metal ball in his hand while dozing in a chair. When sleep overtook him and his grip loosened, the ball would fall and wake him, letting him capture the imagery passing through his mind. Salvador Dali used the same technique with a key and a plate. The hypnagogic state is associated with elevated theta activity and reduced activity in the brain regions responsible for linear thought. Consciousness in this state is loose, associative, and unusually open to novel connections, which may explain why so many people report solving problems they couldn't crack while fully awake. The brain does not learn equally at all times of day. Memory encoding is most efficient in the morning, when alertness is high and the hippocampus is relatively cleared from the previous night's consolidation. By the afternoon, hippocampal capacity is partially saturated, and encoding efficiency declines. Sleep resets this capacity. A study by Matthew Walker's group at Berkeley showed that participants who napped for 90 minutes in the early afternoon showed a 12% improvement in learning ability in the late afternoon, compared to those who did not nap. And those who did not nap showed a 10% deterioration. Sleep is not recovery from cognitive decline. It is the mechanism by which cognitive capacity is actively restored. Targeted memory reactivation is a technique that allows researchers to influence which memories are consolidated during sleep. It works by pairing a learning experience with a sensory cue, typically a smell or a soft sound, during waking hours. When the same cue is presented during slow-wave sleep, the brain's hippocampal replay of the associated memory is enhanced. The memory receives more consolidation resources, emerges stronger the next day, and shows greater resistance to forgetting. This technique is still experimental, but it demonstrates a principle with profound implications. The brain's overnight editorial process is not entirely fixed. It is, at least partially, directable, not through conscious effort, but through the conditions created around sleep. 25 facts in 25 facts. A pattern has emerged that points towards something the field has been working to articulate for years. The brain's capacity to change, to genuinely update the patterns it runs, the emotional weight it assigns to experience, and the habits it automates, is not primarily a function of waking effort. It is a function of sleep. Every technique, every therapy, every practice that leads to lasting psychological change works partly because sleep is consolidating the change overnight. Without the sleep, the gains are temporary. With it, they become structural. The mechanism runs in the dark, without instruction, and it has been running in every sleeping brain for as long as there have been brains capable of learning. That is where the next arc begins. You've been with us for a while now, and your breathing has likely softened without you noticing. A soft subscribe helps another sleepless mind find this sanctuary too. Now, let's pause together, one sleepy soul at a time. Right now, the norepinephrine in your brain is lower than it was an hour ago, not because of anything you did, because you stopped adding to it. That chemical, the one that carries alarm through the system, has a natural flaw, and your body has been moving toward it since the moment you lay down. The question that just opened, about what this mechanism can and cannot reach, about what happens when the loop runs long enough that the brain no longer processes it in a single night, lives in exactly this chemistry. In what happens when the floor keeps rising instead of falling. Notice your breath. The system is already demonstrating its answer. Now we continue. Not all emotional memories are processed equally by the sleeping brain, and the reasons why are only now becoming clear. Recent research has identified that overnight consolidation is selective in a specific way. It preferentially processes memories, carrying what researchers call motivational salience. Memories tied to goals, values, unresolved social tensions, and self-relevant concerns. Memories that feel meaningless receive less consolidation, even if they were intensely emotional. Memories that feel meaningful receive more, even if mildly emotional. The brain is not simply processing what was loud. It is processing what it believes matters. The loop you run at bedtime is, by this definition, something the brain has decided matters. That assessment itself can be changed. The lateral prefrontal cortex plays a specific and underappreciated role in the overnight emotional processing cycle. During waking hours, this region holds multiple pieces of information in mind, while applying reasoning to them. During REM sleep, it remains partially active, but in a mode researchers describe as loosely constrained, capable of making connections across distant memory networks that waking thought, with its demand for coherence, would not easily permit. This is one reason why effective insights into personal problems often arrive in the morning, just after waking. The night's loosely constrained processing has made connections the constrained daytime system had missed. The morning clarity is not coincidence. It is the output of the overnight session. The relationship between REM sleep and fear extinction has direct clinical implications that are reshaping how post-traumatic stress is understood and treated. Research has shown that individuals who dream about a fear-provoking experience, rather than simply sleeping through it, show significantly greater reduction in the fear response the following day. The dream is not merely accompanying the processing, it is part of the mechanism. The brain's recombinatory processing during dreaming places the fearful memory in new, less threatening contexts, gradually reducing its alarm value. Sleep disruption in the immediate aftermath of a traumatic event may interfere with exactly this mechanism, potentially increasing the risk that the memory remains at full emotional intensity. The brain's reward system, centered on the nucleus accumbens and its dopaminergic projections, is deeply intertwined with both sleep and memory consolidation. Memories associated with reward are preferentially consolidated during sleep, a finding replicated across dozens of studies. More recently, researchers have shown that the anticipation of reward before sleep enhances slow-wave sleep quality and increases sleep spindle density. The effect runs in both directions. Better sleep improves the reward system's sensitivity, making positive experiences feel more rewarding. Poor sleep flattens this sensitivity, a phenomenon sometimes called hedonic blunting, making it harder to feel genuine satisfaction from experiences that would otherwise be fulfilling. The anterior cingulate cortex occupies a position in the brain architecturally suited for the overnight work being described here. It sits at the junction of the emotional and cognitive control systems, playing a central role in conflict detection, error signaling, and the integration of emotional experience with rational evaluation. During REM sleep, the anterior cingulate is reliably active. Research suggests it is involved in identifying which emotional patterns are still generating conflict, which memories are producing a mismatch between expectation and experience, and flagging them for deeper processing. The persistent thought loop is, in neurological terms, a conflict signal the anterior cingulate has registered and not yet resolved. Memory reconsolidation fundamentally changed the scientific understanding of how memories are stored and modified. For most of the 20th century, memories were thought to become stable once consolidated. fixed in the architecture of the brain. Then, in 2000, Karim Nader and colleagues at New York University demonstrated that reactivating a consolidated memory renders it temporarily unstable again. During this instability window, the memory can be modified. Sleep appears to play a role in reconsolidation, as well as initial consolidation. Memories that are reactivated and then followed by sleep show greater modification in the direction of emotional neutrality than memories reactivated during waking hours alone. The loop, revisited and followed by sleep, is not the same loop the next morning. The default mode network's role in self-referential processing is directly relevant to the kind of repetitive thought that characterizes insomnia and emotional rumination. When this network becomes overactive, particularly in its connections between the medial prefrontal cortex and the posterior cingulate cortex, it produces the experience of thought loops. The same narrative, revisited with the same emotional coloring, without arriving at new conclusions. Sleep disrupts this overactivity. In rested individuals, the default mode network's connections are recalibrated overnight, reducing the stickiness of self-referential loops. In individuals with chronic poor sleep, this recalibration is incomplete, and the loops tend to be stickier and more persistent across subsequent days. The role of the thalamus in sleep and memory processing is one of the most underappreciated stories in neuroscience. Near the center of the brain, it acts as the relay hub for almost all sensory information, routing signals from the body and the environment to the appropriate cortical regions. During sleep, the thalamus shifts its activity pattern. During slow-wave sleep, it generates the sleep spindles that coordinate hippocampal neocortical transfer. It also acts as a gate, actively blocking incoming sensory signals from disturbing the consolidation process. This is why a sleeping person can remain unaware of sounds that would immediately wake them if the gate were open. The consolidation process is protected by design. Neuroplasticity, the brain's capacity to change its own structure and function, is not uniformly distributed across time. The molecular machinery of plasticity has a rhythm. Brain-derived neurotrophic factor, called BDNF, is one of the proteins most critical to synaptic plasticity, and its production peaks during slow-wave sleep. BDNF promotes the growth of new synaptic connections and facilitates the structural changes underlying long-term memory formation. A night of poor, slow-wave sleep is a night in which BDNF production is reduced, and structural changes either happen incompletely or not at all. The molecular window for overnight change requires sleep of sufficient depth to open. Sleep and language are more deeply connected than most people appreciate. Linguistic memory, vocabulary, grammar patterns, and the semantic networks that give words their meaning is consolidated during sleep in ways that procedural and episodic memory are not. Studies of second language learners show that sleeping after a learning session accelerates vocabulary retention. More relevant here, the internal monologue, the language the brain uses to narrate the self, is itself a form of linguistic memory. The words you habitually use to describe your situation and your worth are stored as semantic patterns. Those patterns are consolidated during sleep. they are also, in principle, plastic, subject to the same overnight remodeling, given the right conditions. The concept of state-dependent memory offers a partial explanation for why some emotional patterns feel impossible to change while awake. Memories are most easily retrieved in the same physiological and emotional state in which they were formed. A memory encoded during high arousal, anxiety, anger, threat, is most easily retrieved during subsequent high arousal states. This creates a feedback loop. The anxious mind retrieves the most anxiety-provoking memories, which increases anxiety, which makes more anxiety-provoking memories accessible. Sleep breaks this loop by processing emotional memories in the absence of the original arousal state. The low norepinephrine environment of REM sleep allows the brain to examine what high arousal waking could not examine calmly. The interaction between sleep and the gut-brain axis has emerged as a significant area of research in the past decade. The enteric nervous system, the network of hundreds of millions of neurons lining the gastrointestinal tract, communicates bidirectionally with the brain via the vagus nerve. The gut microbiome influences this communication by producing neurotransmitter precursors, including tryptophan, a precursor to serotonin and ultimately to melatonin. Disrupted sleep alters gut microbiome composition within days, and disrupted gut microbiome composition impairs sleep quality. The overnight consolidation process is embedded in a broader biological system, one that includes nutrition, microbiome health, and the enteric nervous system. The brain reprograms in the context of the body it inhabits. The study of sleep in non-human animals has revealed that consolidation processes appear throughout the animal kingdom, suggesting deep evolutionary origins. Rats show hippocampal replay during sleep that mirrors the sequences they ran in mazes during the day. First shown by Matt Wilson and Bruce McNaughton in 1994. Songbirds rehearse newly learned songs during sleep, with the motor neurons responsible for singing activating in the same patterns as during daytime practice. Zebrafish show sleep-dependent synaptic remodeling that closely parallels mammalian studies. The overnight rewrite is not a uniquely human phenomenon. It is one of the most ancient and conserved functions in the history of nervous systems. The relationship between sleep and creativity, specifically the capacity to arrive at solutions unavailable during waking analytical thought, has been documented in multiple experimental paradigms. One of the most replicated findings is the incubation effect. Problems that remain unsolved after sustained waking effort are often solved quickly after a period of sleep, without any additional conscious work. Studies that compare sleep incubation to equivalent periods of quiet waking rest consistently find sleep superior. The specific stage most associated with creative insight is REM sleep, where loosely constrained associative processing allows connections across distant memory networks that analytical thought does not readily make. The solution that arrives in the morning was assembled overnight, in the dark. The brain's overnight editorial process is not neutral about identity, self-concept, the network of beliefs, narratives, and emotional associations that constitute a sense of who you are, is a form of semantic and episodic memory stored across the medial prefrontal cortex, hippocampus, and posterior cingulate cortex. Like all long-term memories, it is subject to overnight remodeling. Positive experiences inconsistent with a negative self-concept tend to be remembered less well than experiences that confirm it. But sleep appears to modulate this bias. Individuals who sleep well show a greater capacity to update their self-concept in response to new experience. The identity is not fixed. It is a living pattern, and sleep is part of what keeps it alive. There's a quietness settling in now. Something in the pace has changed. Take a slow breath. Notice how the facts have been moving through you rather than at you, each one landing somewhere a little deeper than the last. We're wandering through the architecture of the sleeping mind together. You and I, in the quiet hour it was built for. We'll keep going, slowly. The consolidation of procedural memory, the kind that underlies skills, routines, and automatic behaviors, follows a different pathway than declarative memory. But it is no less sleep-dependent. Procedural memories are consolidated through the striatum and cerebellum, with activity concentrated in stage 2 sleep, when spindle density is highest. This is directly relevant to reprogramming habitual behavior, because habits are procedural memories. The reactive response to a specific trigger, the automatic reach for a familiar coping behavior. These are stored in the procedural system. They cannot be rewritten by declarative intention alone. They require sufficient stage 2 sleep, repeated over multiple nights, with a new behavior practiced consistently enough to generate the signal the brain decides to consolidate. Intention setting before sleep, articulating clearly what you want to process, learn, or change, has measurable effects on what the brain prioritizes during overnight consolidation. This is not mystical. It is attention-dependent encoding. The brain consolidates what was most salient during the hours before sleep. What you attend to, what you emotionally engage with in the final hours before bed, creates a consolidation cue. Studies on pre-sleep cognitive activity confirm that deliberately reviewing positive experiences or new learning in the hour before sleep enhances their consolidation. The direction of attention shapes the direction of the overnight edit. The subconscious mind does not ignore the last message it receives before the lights go out. The role of body temperature in sleep architecture connects directly to the depth of slow-wave sleep where consolidation occurs. Core body temperature follows a circadian rhythm, peaking in the late afternoon and declining through the evening. The decline itself, not just the low temperature, but the active cooling, is one of the primary signals that triggers sleepiness and facilitates the transition into deep sleep. A faster temperature drop correlates with faster sleep onset and more time in slow-wave sleep. This is why a warm bath taken 90 minutes before bed, not immediately before, paradoxically improves sleep. It causes rapid surface heat loss afterward that accelerates the core temperature decline. Thermoregulation is part of the machinery that makes the overnight edit possible. Implicit memory. Memory for things you know without knowing you know them, is deeply consolidated during sleep in ways that explicit memory is not. The most striking demonstration is the serial reaction time task. in which participants press buttons in a sequence containing a hidden, repeating pattern. After sleep, participants show significantly improved performance on the hidden pattern, even though they cannot consciously report that a pattern exists. The improvement does not come from additional practice. It comes from sleep. The brain extracted the pattern and updated the procedural system accordingly, all without conscious awareness that learning was happening. What changes in sleep is not always what you know. The social dimension of sleep deprivation is among the most consequential of its effects. Studies at the Max Planck Institute and the University of California, Berkeley, have shown that sleep-deprived individuals are perceived as significantly less trustworthy and less approachable by observers in interactions as brief as 60 seconds. Sleep-deprived individuals also show reduced activity in the brain regions responsible for empathy, prosocial behavior, and the recognition of subtle social signals. Inadequate sleep affects the quality of every social interaction, which shapes the new emotional memories being encoded each day. The pattern that sleep is trying to process is being partially regenerated by the social environment that poor sleep helps create. The timing of light exposure is one of the most powerful environmental regulators of sleep architecture. The suprachiasmatic nucleus, a tiny cluster of about 20,000 neurons in the hypothalamus, is the brain's master clock. It synchronizes all biological rhythms to the external light-dark cycle, light containing short wavelengths. The blue light prominent in screens and LED lighting suppresses melatonin production, even at low intensity. Melatonin is not what makes you sleep. It is the signal that tells the brain when darkness has arrived and the overnight program should begin. Disrupting that signal delays the program. The editorial session starts late and may not finish before morning. The hippocampus and prefrontal cortex undergo a specific functional reorganization during long-term memory consolidation that takes weeks, not hours. Immediately after learning, a memory depends heavily on the hippocampus for retrieval. Over multiple sleep cycles across many nights, it is gradually transferred to the neocortex, where it becomes integrated with existing knowledge networks and can be retrieved without hippocampal involvement. This process, called systems consolidation, explains why behavioral change is not instantaneous, even with consistent sleep. The pattern being rewritten is distributed across multiple brain regions and consolidated progressively. Multiple consecutive nights of good sleep produce changes that are qualitatively different, more structural, more stable, more resistant to reversal under stress. The study of people who report minimal dream recall reveals something counterintuitive about dreaming and overnight emotional processing. For many years, it was assumed that people who rarely remember dreams were simply not dreaming. Research using polysomnography established that virtually all people dream during REM sleep, regardless of recall. People who do not remember their dreams are not failing to dream. They are failing to wake during or shortly after REM sleep, when dreams are most accessible to recall. The processing still occurs. The emotional recalibration still proceeds. Dream recall is not a measure of how much processing is happening. It is a measure of how close to waking the processing ends. The adenosine system is the brain's primary homeostatic sleep pressure mechanism. Adenosine is a byproduct of neural activity. Every time a neuron fires, adenosine accumulates in the extracellular space. Over a waking day, adenosine levels build steadily, creating increasing sleepiness. When you fall asleep, adenosine is cleared. Slowly, during light sleep. More rapidly, during deep sleep. Caffeine works by blocking adenosine receptors, creating alertness without actually reducing adenosine accumulation. This is why the tired feeling returns forcefully when caffeine metabolizes chronically elevated adenosine. From consistently shortened sleep is one of the biochemical signatures of cognitive impairment associated with poor sleep. Its overnight clearance is part of what makes waking feel genuinely fresh rather than merely functional. 50 facts in The Picture is This. Reprogramming the subconscious mind is not a matter of willpower, affirmation, or technique applied while awake. It is a biological process, specific in its mechanisms, dependent on sleep stages, regulated by neurochemistry, and constrained by the conditions the sleeping environment provides. The central question: how does your sleeping brain quietly rewrite the emotional weight of what you carry? Has a partial answer. Through spindles, slow oscillations, RM neurochemistry, and the overnight recalibration of synaptic connections across the hippocampus and neocortex. What the second half follows. What does the brain do when the emotional pattern is too old or too reinforced to process in a single night? What just opened? The question of what the brain does when the loop is older than a single night can reach is not only a neuroscience question. You may be carrying a version of that right now. Something that has returned enough times that the body no longer expects it to resolve. That has been running so long that it has begun to feel like character rather than pattern. That is not failure. That is simply a pattern that has had more nights of reinforcement than of processing. The second half of tonight follows what happens to that pattern. Over time, across many nights, with the right conditions in place. Notice your breath. Notice that it keeps moving, even when the question doesn't close. Now we continue. The concept of memory, traces, or engrams, refers to the physical changes in neural tissue that constitute a stored memory. For most of the 20th century, the engram was theoretical. Researchers led by Susumu Tonegawa at MIT identified and even artificially activated specific engram cells in mice, neurons whose synaptic changes correspond to specific memories. Memories live in the physical structure of the brain, changes in which neurons connect to which other neurons, and how strongly. The emotional weight attached to a memory is encoded in these connections. Changing the emotional weight means changing the connectivity. Changing the connectivity at scale requires sleep. Chronic stress produces structural changes in the brain that directly impair the overnight consolidation process. Prolonged exposure to cortisol reduces the volume of the hippocampus through dendritic atrophy. The branching extensions of hippocampal neurons that receive synaptic input gradually retract. A smaller, structurally compromised hippocampus has reduced capacity for new memory encoding and reduced efficiency in the overnight transfer process. Research has shown that hippocampal volume loss from chronic stress is partially reversible. With sufficient sleep, exercise, and reduced stress load over time, the architecture can rebuild. The spindles return. But this reversal is not immediate. It is measured in weeks and months, not days. The relationship between sleep quality and the persistence of intrusive thoughts is consistently observed in clinical populations. People with generalized anxiety disorder, post-traumatic stress, and obsessive-compulsive disorder. Poor sleep does not simply fail to process intrusive thoughts. It may actively reinforce them. During fragmented sleep, the brain enters and exits REM sleep repeatedly, without completing the full processing cycle. The emotional charge of the intrusive content is partially accessed but not fully resolved. The next day, the content returns, with its charge partially intact, and often with slightly elevated anxiety. The result is a progressive tightening of the loop across nights, rather than a loosening. The evidence for sleep's role in psychological resilience, the capacity to recover from adversity without lasting damage, is substantial and growing. Studies following individuals through major life stresses consistently find that pre-existing sleep quality is one of the strongest predictors of whether the person develops chronic psychological symptoms. Those who were sleeping well before the stressor tend to process it over subsequent nights and return to baseline within weeks. Those who were sleeping poorly show significantly elevated rates of persistent anxiety, depression, and intrusive symptomatology. Sleep is not a passive bystander in psychological recovery. It is the mechanism through which recovery actually happens. The brain's capacity for overnight emotional processing appears to diminish with age, but the mechanisms of this decline are more complex than simple biological decay. Slow-wave sleep decreases markedly across the lifespan, with the steepest decline between young adulthood and midlife. By the mid-50s, many people are getting 50% or less of the slow-wave sleep they had at 25. Sleep spindle density also decreases. The consequence is not that the brain stops consolidating during sleep. It does so less efficiently. Some of that architectural decline is modifiable through exercise, consistent sleep timing, and the reduction of sleep-fragmenting behaviors. Music and acoustic stimulation during sleep have emerged as a non-pharmacological tool for enhancing slow-wave sleep and the consolidation processes within it. Research by Jan Born's group at the University of Tübingen has shown that brief bursts of pink noise, synchronized with the slow oscillations of deep sleep, significantly increase slow oscillation amplitude and enhance overnight memory. Consolidation. The synchronization is the critical element. Random noise has no effect, and even precisely timed noise slightly out of phase with the oscillations reduces consolidation. The timing must match the upstate of the slow oscillation, the moment of neural activation in the cycle, to amplify rather than disrupt. The placebo effect in sleep is real, measurable, and neurologically significant. Studies in which participants were told they had slept well, regardless of how they actually slept, showed improved cognitive performance compared to those told they had slept poorly. The mechanism appears to involve the expectation of restoration, activating some of the same neurological pathways as actual restoration. Anxiety about sleep quality, sometimes called orthosomnia, has been identified as a driver of insomnia, partly through this mechanism. The belief that sleep was insufficient activates a mild stress response that impairs the very cognitive function, whose decline then confirms the belief. The interaction between exercise and sleep quality is one of the most consistently demonstrated relationships in sleep research. Moderate aerobic exercise, equivalent to a 30-minute brisk walk, increases slow-wave sleep on subsequent nights, elevates BDNF levels, and reduces the time it takes to fall asleep. Morning and afternoon exercise reliably improves sleep. Vigorous exercise within 2 to 3 hours of bedtime may delay sleep onset in some people, though recent research suggests this effect is smaller than previously thought. The pathway through which exercise improves slow-wave sleep likely involves adenosine clearance, thermoregulatory effects, and BDNF-mediated synaptic plasticity. The body's movement during the day is part of what makes the night's work possible. The neuroscience of forgetting is, paradoxically, as important to overnight processing as the neuroscience of remembering. Forgetting is not a failure of the memory system. It is an active process, regulated by specific molecular mechanisms. The protein CPEB3, identified by Kausic-C at the Stowers Institute for Medical Research, plays a role in determining which synaptic changes are maintained and which are allowed to decay. During sleep, the balance between consolidation and forgetting is actively managed. The things you forget after sleep are not accidents. They are the things the brain determined were better forgotten. What remains is what the system decided was worth carrying. The brain's consolidation of emotional memories is modulated by a molecule called neuropeptide Y, which has received significantly less attention than serotonin or dopamine despite its central role in stress resilience. Neuropeptide Y is released in the amygdala and hippocampus during recovery from stress and during slow-wave sleep. It reduces the amygdala's reactivity, dampens the stress hormone response, and promotes the consolidation of positive emotional associations. Individuals with naturally high neuropeptide Y activity show greater resilience to traumatic stress. Their emotional memories are processed more efficiently, and the stress response habituates more quickly. It is one of the molecules through which sleep builds the biological architecture of emotional resilience. Social defeat, the experience of being dominated, humiliated, or chronically subordinated, produces some of the most persistent emotional memories in both animal models and human populations. Research using rodent models has shown that the overnight consolidation period following a social defeat is critical to whether the behavioral effects, avoidance, reduced social engagement, and anhedonia, persist or resolve. Animals allowed to sleep normally after social defeat show substantially faster recovery. What differs is how the brain ultimately categorizes the experience as a past event or as an ongoing condition. These are animal model findings. Human parallels are plausible, but require further study. The relationship between sleep and the immune system has direct implications for emotional processing. because the immune system and the brain communicate continuously through cytokines, small signaling proteins that also influence mood, motivation, and cognitive function. During slow-wave sleep, pro-inflammatory cytokine activity is at its highest, and anti-inflammatory processes are most active. When sleep is disrupted, both immune function and cognitive emotional consolidation decline in parallel. This is one reason why illness tends to produce fatigue, low mood, and cognitive impairment. The system is diverting resources to immune maintenance, leaving less capacity for the emotional work that ordinarily runs in the same window. The anterior hippocampus and posterior hippocampus have distinct functional profiles, both relevant to overnight emotional processing. The posterior hippocampus is more involved in precise contextual memory, the specific details of where, when, and how something happened. The anterior hippocampus is more involved in emotional memory, generalization, and the extraction of patterns across multiple experiences. During overnight consolidation, the posterior provides detailed replay, while the anterior extracts the emotional themes running across them. This is one mechanism through which sleep converts specific emotional episodes into more general emotional knowledge. The difference between remembering a frightening event and acquiring a broader sense of threat or safety in a domain. The study of sleep in infants and young children reveals that consolidation processes are present from the earliest weeks of life. Infants spend between 50 and 80% of their sleep time in REM sleep, compared to roughly 20% in adults. This elevated REM time reflects the enormous consolidation demands of a brain encoding language, social patterns, motor skills, and emotional templates simultaneously. The emotional templates formed during early childhood, the internal working models of attachment, safety, and self, are among the most deeply encoded patterns in the brain, resistant to overnight recalibration in adulthood. But resistant does not mean fixed. The concept of sleep inertia, the grogginess experienced immediately upon waking, offers a window into the transition between consolidated and non-consolidated states. Sleep inertia is most pronounced when waking occurs during slow-wave sleep, when consolidation is most active, and least pronounced at the end of a REM cycle. During sleep inertia, and the prefrontal cortex is among the last regions to return to full waking function. Decision-making, impulse control, and emotional regulation are all temporarily impaired. The emotional tone of the first waking minutes partly reflects what was most actively being processed at the moment of waking. Lucid dreaming, being aware that one is dreaming while remaining within the dream, provides a rare experimental window into the relationship between conscious awareness and overnight processing. Lucid dreamers show elevated prefrontal cortex activity during REM sleep, suggesting REM's loosely constrained processing is at least partially compatible with maintained self-awareness. Research has explored whether lucid dreaming can be directed toward the processing of specific emotional content, whether awareness within a feared dream can be used to deliberately alter the outcome. Early studies suggest modest but measurable benefits. The question of how much conscious intention can influence the overnight process remains genuinely open. The precision of the overnight rewrite depends on what researchers call sleep consolidation window integrity, the degree to which the sleep period is continuous and architecturally complete. Fragmented sleep disrupts the natural progression through sleep stages, preventing later REM cycles from reaching their full duration, and interrupting the slow oscillation sequences that coordinate hippocampal replay. The architecture matters as much as the duration. A night spent in and out of partial waking, exactly what anxiety about sleep tends to produce, is a night in which the consolidation process runs incomplete. The relationship between sleep and autobiographical memory, the coherent narrative of one's own life, is one of the most profound aspects of what overnight consolidation does. Autobiographical memory is not a passive archive. It is a continuously edited narrative, subject to revision at every retrieval. Each time you remember something from your past, the memory is briefly destabilized, updated in light of current knowledge and emotional state, and reconsolidated. Sleep plays a role in this updating process, integrating the most recent revision with the broader autobiographical system. The self-concept is being reauthored slightly every night, and sleep is part of what edits it. The neurochemical differences between sleep stages explain why different kinds of processing require different stages. Acetylcholine is high during REM sleep and waking, low during slow-wave sleep. Norepinephrine is high during waking and at its lowest during REM. These profiles determine what kinds of synaptic changes are possible in each state. High acetylcholine during REM supports the associative, cross-network processing that characterizes dreaming. Low norepinephrine during REM creates the conditions for emotional memory processing without reactivating the threat response. Low acetylcholine during slow-wave sleep supports the directed hippocampal to neocortical transfer. The chemistry is not incidental. It is the machinery. The interaction between social support and sleep quality is bidirectional and significant. People who feel more socially connected tend to sleep better, partly through reduced cortisol and partly through the co-regulation effects of the parasympathetic nervous system, activated by feelings of safety and belonging. People who sleep better tend to maintain social connections more successfully through the improved emotional regulation that good sleep supports. The overnight processing of social memories occurs more completely in individuals who feel safe enough to sleep deeply. The feeling of safety is not merely psychological comfort. It is a physiological condition that enables the brain to enter the stages where the deepest processing occurs. The relationship between meditation practice and sleep quality is one of the more consistently supported findings in the contemplative neuroscience literature. Regular mindfulness meditation, practiced during waking hours, is associated with improved sleep quality, increased slow-wave sleep, reduced sleep onset latency, and reduced nighttime waking. The mechanism is not primarily through relaxation at bedtime, but through sustained changes in default mode, network regulation, and amygdala reactivity that accumulate across months of consistent practice. Long-term meditators show reduced activity in the default mode network's self-referential loops and reduced amygdala reactivity to emotional stimuli. Exactly the changes that support more efficient overnight processing. Polyvagal theory. proposed by Stephen Porges, offers a framework for understanding how the autonomic nervous system's state at sleep onset influences, overnight, processing quality. The theory describes 3 broad states: ventral vagal, associated with social engagement and safety; sympathetic, associated with mobilization and threat; and dorsal vagal, associated with shutdown. Deep, restorative sleep with intact slow-wave architecture occurs most readily from the ventral vagal state. Entering sleep from a sustained sympathetic state may compress the slow-wave stages and fragment REM. Note, polyvagal theory remains partially contested in the scientific literature. Its clinical applications are under active investigation. The role of omega-3 fatty acids in sleep quality is one of the more nutritionally specific relationships in sleep research. The primary omega-3 fatty acid in the brain is essential to cell membrane fluidity in neurons and to the function of receptors involved in both sleep architecture and memory consolidation. Studies have found correlations between blood DHA levels and slow-wave sleep duration, and between DHA supplementation and improved sleep quality in adults with low baseline omega-3 status. The quality of the brain's structural fat influences the efficiency of the synaptic processes that consolidation depends on. The concept of sleep pressure, the homeostatic drive towards sleep, is regulated through 2 interacting systems: the adenosine system, which tracks accumulated waking activity, and the circadian system, which tracks time of day. These 2 systems normally align, producing a strong consolidated sleep period in the evening. When they are misaligned, through irregular sleep schedules, shift work, or the sleep architecture suffers. The slow-wave sleep and REM cycles that consolidation depends on require not just the right amount of sleep, but sleep at the right biological time. Consistent sleep timing is a condition for the overnight edit to run in full. The science assembled across these 75 facts points toward a conclusion that is both humbling and liberating. The brain is already doing the work. Every night, without instruction, without effort, without awareness. The system that evolved to maintain the coherence and adaptability of the mind runs its maintenance cycle. It processes what was charged. It softens what was raw. It transfers what was fragile into architecture that can hold it. Sleep is not passive rest. It is the brain's only window to safely dissolve what you can't let go of while awake. The remaining facts carry a different quality, not as argument, but as experience, as what it feels like to carry something that sleep has already begun to quietly release. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. The slow oscillations moving through your cortex right now are following the same rhythm they have followed every night of your life. A wave of activation, a wave of silence, a wave of activation again. You don't create them. You don't maintain them. They simply run, like your breath. Inhale, exhale, inhale. A small cycle within the vast architecture of a system that has been running far longer than your worry about it has. You are not separate from this process. You are it. Let everything continue in its own order. unhurried, unresisting, simply happening. We're almost there now. The loop you were running before you lay down tonight is already being touched. Not by anything you did, by the simple fact that you stopped moving and let the system do what the system does. That is enough. The brain does not need a perfect environment to begin processing. It needs only sufficient quiet and sufficient time. Both are here now. Every night you have ever slept through a difficulty, every morning you woke and found that something felt slightly less heavy than it had the night before. That was not time doing the work. That was sleep doing the work. Time alone does not heal. Sleep within time does. The passage of days provides the opportunity. The sleeping brain does the processing. The hippocampus replays the day's events during slow-wave sleep in a sequence that roughly mirrors the order in which they occurred, but with the emotional tags reorganized. What felt most threatening in the afternoon may be processed most thoroughly in the early night. What was unresolved may be revisited multiple times. The sequence is not linear and not complete. The brain selects, but it selects toward resolution when the conditions allow. REM sleep does not arrive all at once. It comes in cycles, each one longer than the last, each one reaching deeper into the night. The final REM cycle of a full night's sleep is sometimes the longest and most neurochemically complete, the most norepinephrine depleted, the most associatively unrestrained. The mornings after the longest, latest sleep often carry the softest emotional residue. This is why the thought that returns every night is not evidence of a broken system. It is evidence of a system prioritizing. The brain is returning to it because the brain has assessed it as unfinished. That assessment is the beginning of processing, not the failure of it. The return is the work. It only feels like circling. From the outside of the system, it is approach. The body holds what the mind cannot finish processing in a given waking day. Muscle tension in the jaw, the shoulders, the abdomen. These are the somatic signatures of emotional material the brain has not yet released. During the descent into slow-wave sleep, muscle tone decreases systematically throughout the body, releasing the physical holding that the day accumulated. The body's letting go and the brain's processing run in parallel, each enabling the other. The slowest thoughts you will have today are the ones that arrive in the hypnagogic threshold, the edge of sleep. They are not your worst thoughts. They are your most loosely organized thoughts, freed from the demand for coherence. Sometimes they are strange. Sometimes they are unexpectedly kind. Sometimes they are simply quiet. Whatever arrives at that edge is the mind transitioning from the mode it was built for waking to the mode it was built for sleeping. Emotional memories are not stored as static files. They are reconstructed every time they are accessed, and the reconstruction changes slightly with each retrieval. The version you carry of a difficult memory is not the original event. It is the most recent reconstruction, shaped by every night's processing that has occurred since the event. Sleep has already been editing that memory. It began editing it the first night after it occurred. It has not stopped. The conditions that make overnight processing most complete are not exotic. They are simple. a consistent sleep schedule, sufficient duration, a sleeping environment cool enough to support core temperature decline, darkness sufficient to allow melatonin release, and a nervous system that feels safe enough to enter deep stages. Safety, in this context, is biological. It is low cortisol, low norepinephrine, and parasympathetic dominance. This is not a metaphor. It is a measurable, physiological state. The brain's capacity to process and eventually release a painful memory does not require the memory to be understood, explained, or forgiven during waking hours. Understanding and forgiveness can follow the release, but they are not prerequisites for it. The release is physiological before it is psychological. The chemistry changes first. The softening of the emotional charge comes first. The meaning-making that follows is, in part, the conscious mind catching up to what the sleeping brain has already done. Sleep spindles are most dense in the period surrounding the transition from waking to stage 2 sleep, and in the second cycle of the night. They are brief, fast, and precise, while the slow oscillations are wide, sweeping, and architectural. Together, they coordinate the hippocampal to neocortical transfer process. When you lie still and stop generating the noise of waking thought, the spindles begin. The transfer begins. It does not require your participation. It requires only your stillness. Brief gratitude practices before sleep. Deliberately recalling 2 or 3 things that went well during the day have been associated with reduced pre-sleep cognitive arousal, increased sleep duration, and improved sleep quality. The mechanism likely involves the selective priming of positive emotional memory for consolidation, partially counterbalancing the brain's overnight negativity bias. What you attend to in the final quiet hour creates the consolidation cue for the night. Attending to what was good does not deny what was difficult. It ensures the brain processes both. The experience of waking at 3 or 4 in the morning has a neurological basis. It corresponds to the end of the first major slow-wave sleep period and the transition toward the longer REM cycles of the second half of the night. The brain is closer to waking consciousness at this hour. If emotional material was not fully processed in the first half, it is more likely to surface here. This is not malfunction. This is the brain approaching the material it most needs to work on. The word reprogram implies a deliberate override, someone at a console, entering new instructions. The brain does not work this way. The overnight rewrite is not a replacement. It is a gradual recalibration, a slow shifting of the weights assigned to different patterns, carried out across many nights, through mechanisms that are chemical, architectural, and rhythmic. The pattern does not disappear. It softens. The charge reduces. The loop slows. And eventually, what had felt inescapable becomes simply a memory of how things once were. Animals deprived of REM sleep following a traumatic experience show persistent fear responses that animals allowed normal REM do not show. The REM sleep is not removing the memory of the trauma. It is processing the emotional weight attached to it, completing the fear extinction cycle initiated during waking. The trauma is still known. It is simply no longer alarming in the same way. The sleeping brain does not erase. It completes. The relationship between sleep and hope, the expectation that the future can be different from the present, has been examined in research on learned helplessness and depression. Individuals with disrupted sleep architecture show reduced activity in the medial prefrontal cortex regions associated with positive future projection. The capacity to imagine a better outcome is partly a function of the brain's overnight recalibration. Without sufficient processing, the past tends to feel more fixed. Sleep does not generate hope, but it maintains the architecture that makes hope neurologically possible. The slowest, deepest breath you take during the night occurs during slow-wave sleep, when the body's metabolic rate is at its lowest and the autonomic nervous system is most fully in its restorative mode. The respiratory rate drops to between 8 and 12 breaths per minute. The heart rate slows. Blood pressure falls. The entire physiological system settles into the rhythm that the consolidation process requires. The body's stillness is not the absence of activity. It is the condition under which the most significant activity of the 24 hours occurs. The brain region, called the insula, tucked within the lateral sulcus, is involved in interoception, the sensing of the body's internal state. During REM sleep, the insula remains active, continuing to monitor the body's signals, even as external awareness decreases. This ongoing monitoring is thought to contribute to the integration of somatic and emotional experience, the process by which the physical residue of emotional events is gradually metabolized alongside the cognitive content. The body and the brain process together in the dark. The scientific definition of consolidation has expanded to include not only the stabilization of individual memories, but the integration of new experience into existing knowledge networks. Consolidation is not merely filing, it is the reorganization of the entire filing system in light of what is new. Every night, the brain asks not only what happened today, but what today means in the context of everything that came before. The answers accumulate slowly, across many nights. The accumulated answers are what we call wisdom, and also, more quietly, healing. The most persistent emotional patterns, the ones that have survived decades of waking effort, are the ones consolidated most thoroughly over the most nights. Their persistence is not evidence that they cannot be changed. It is evidence that change will take the same currency that built them: time, sleep, and the gradual accumulation of new experience. The brain eventually prioritizes. The loop runs as long as the brain believes it is the most relevant pattern available. Sleep, given sufficient time and new input, updates that belief. The brain does not distinguish between waking intention and what it consolidates. It consolidates what was emotionally salient and frequently activated, regardless of whether those activations were deliberate or involuntary. Worrying about a pattern reinforces it slightly, even while trying to eliminate it. But genuinely engaging with new experiences, new relationships, and new responses, not as technique, but as living, gives the brain new material to consolidate. New patterns grow from use. The old ones do not disappear. They simply recede as the new ones accumulate. Tonight is one night in a long sequence. The process does not complete in a single session. The brain that has been building this hour's facts has also been on every previous night, running its own processing cycle, some of which produced the changes that made tonight's understanding possible. The sequence continues after tonight. The consolidation of this hour's content will happen across the next several nights. What you understand now will settle more deeply in the coming days than it does in the morning. The gentlest thing the brain does is the thing it does most consistently. It returns every night to what was difficult, not to extend the suffering, but to process it. The return is care. The replay is the mechanism of healing. The loop that keeps you awake is the brain doing, imperfectly, what it is built to do. Sleep takes it from there. Sleep has always taken it from there. The answer to the question of how the sleeping brain rewrites emotional weight is not located in any single fact from this hour. It is distributed across all of them, across the spindles and the slow oscillations, the REM neurochemistry, the hippocampal replay, the neocortical integration, the synaptic recalibration, and the molecular signaling that ties them together. The answer is a system, and you are already inside it. Sleep is not passive rest. It is the brain's only window to safely dissolve what you can't let go of while awake. Not because you earned it, not because you figured it out, because you lay down, and the system did what the system does. You do not need to understand it. You do not need to direct it. You only need to let the night do what the night was built for. It already has. 100 facts ago, we were asking how the sleeping brain rewrites the emotional weight of what you carry. The answer that assembled was not what the word reprogram usually promises. It was quieter, more specific, and more reliable than any technique. We followed the norepinephrine from its waking peak to its floor in REM, watched the hippocampus replay the day at speed, and traced the slow oscillations as they coordinated the transfer of what was fragile into the architecture of what can hold it. What began as a question about the subconscious mind became an answer about a biological process that runs every night, without effort, without instruction, and has already begun. The night was never empty. It was always working. Sleep is not passive rest. It is the brain's only window to safely dissolve what you can't let go of while awake. You carry that knowledge differently now. Not as information, as permission. The loop that returns tonight is already inside the system that processes it. That is enough. In these final minutes, take the deepest breath you can. As deep as possible. Think about consciousness itself. Yours. Mine. Everyone listening. All awareness. Everywhere. Perhaps all connected in ways we don't yet understand. Think about how the subconscious processing of every sleeping mind on Earth is running right now. In this hour, in this darkness, each one doing its quiet work, each one moving through the same stages, each one releasing something that the day could not release. You are not alone in this process. Let your entire being dissolve into the ocean of consciousness, into dreamless rest, into the space before thought, into the place where the work is already done. No boundaries left. only peace. Perhaps the science of what sleep quietly does brought some ease to a mind that has been carrying something, a soft like, a gentle subscribe, or a quiet share, carries that ease to another sleepless mind, still searching for where to rest. One quiet tap, one sleepy soul at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight. You can allow these thoughts of what the sleeping brain quietly does to fade now, like the last light leaving a room before sleep. Slowly, without ceremony, leaving only the stillness behind. Let your breathing deepen. Let your body feel heavier, as if the architecture of the night itself is settling around you, anchoring you gently to the bed. If sleep comes, let it carry you like the slow oscillation that began when you lay down, smoothly, inevitably, into the place where time and weight no longer matter. Sleep science has been exploring the architecture of the sleeping mind across many hours. The next hour follows a question this one didn't have time to finish. What the brain does with the emotional residue it cannot process in a single night, and how the pattern finally shifts. That hour is waiting whenever you are ready. But if your eyes are already closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the slow oscillations will continue. The spindles will return. The system will run again. But tonight belongs to stillness. Rest well, quiet one. And remember, sleep is the brain's only window to safely dissolve what you cannot let go of while awake, where science becomes the softest place to rest. Good night.